Hello, my name is Chris Allen, and my final project is on pipes and multiple UARTs. Some of the unique aspects of my operating system are its support for standard I/O, the ability to redirect input and output via pipes, support for named pipes, and support for device-independent interrupt-driven UART 2, 3, and 4. UART 4 was used to interface to a text-to-speech module, and UART 3 has a second shell implemented on it. Device-independent pipe support in my system works very much like a cross between a file device and a serial device. It's similar to a file device because it allocates buffer data dynamically. It's similar to serial devices because the buffer it allocates is circular with a reader and a writer. The pipe is initialized when it's first opened. That means the counters are reset and the buffer memory is allocated. And it's important to note that this only occurs the first time a user calls open. Subsequent calls to open do not reinitialize the buffer. When pipe read is called, it works like a UART in that the system blocks until data is available. Once available, the data is retrieved from the circular buffer. Likewise, when pipe write is called, the system blocks if the buffer is full. Once space is available, data is written to the buffer. Create pipe creates a temporary unnamed pipe. The pipe actually does have a name. It's an auto-generated unique name that is not needed to use the pipe, as only the handle is required. The unique name is generated using the 64-bit millisecond timer implemented in the OS. So there's a P character followed by the higher order 32 bits and then the lower order 32 bits of that 64-bit time. This gives the accuracy of the unique name to about a millisecond. And I found during my testing that it is usually 2 or 3 milliseconds in between directly calling create pipe one right after the other. So I also added a yield and then to try again if the name happened to not be unique. Create named pipe creates a more permanent pipe with the user supplied name. I also added an MP shell command so that you could make named pipes from the command line. During the release of a named pipe, the system blocks the writer from releasing until all bytes have been read. This I did for testing purposes, and we'll see how this operates here shortly. Pipe release, when the last user closes the pipe, the counters are reset and the dynamically allocated buffer memory is freed. And again, this only happens when the last user closes. The buffer size, which is established when the pipe is created, is not reset here, and that buffer size is used to reinitialize the buffer if the pipe is reused and open is called again, which generally doesn't happen for unnamed pipes, but could very well happen for named pipes. The pipe character can be used to redirect standard I/O from the shell. This allows one program to pipe its output to the input of another program. And here you can see the structure that I have for my command line interface. This is the structure that gets populated as the command line is parsed. So what I've done is I've added a next to this so that every time I encounter a pipe during parsing, I create another command definition entry in my linked list. When I go to execute a command line that was entered that has a next command line to it, I create a temporary unnamed pipe. The pipe is then opened for both reading and writing. The next command standard in is assigned the read handle on the pipe, and the current command standard out is assigned the write handle on the pipe. The next process is then spawned. The current command is then run. After the current command is run, the system waits for the next process to complete. It then closes the handles and removes the temporary pipe. Lastly, it resets standard out. Multiple UARTs have been added by way of a device independent structure. So here you can see my minor device structure where I've got the baud rate, the base pointers, and the IRQs for the various UARTs. Also present are structures for the I/O buffer and interrupt counters. COM2, 3, and 4 were supported. Here you can see the init uarts function that gets executed when the file system gets started, so you can see where those are created. COM2 was the shell, shell 1, COM3 was shell 2, and COM4 was available for use, and I implemented a user program for working with the EMIC2 text-to-speech board. Here's a picture of my hardware, and I have to thank Dr. Frankel for helping me map out the UARTs and the pins. It took quite a long time to do. It was a big effort. So thank you very much for that. You can see my EMIC2 in the lower left and the RS-232 converter, which I needed because I was going from the CMOS 3.3 volt I/O to the RS-232 I/O. So that converted the voltages. Two shells, one on UART2 and one on UART3, and the way they were implemented, I could easily add additional ones based on hardware. The standard I/O is tracked on a per shell basis. So here you can see my shell config structure where I've got the UART name, the shell index, and then the default inputs and outputs, as well as the current inputs and outputs. The default is used so that in order to reset the current back to their default settings when needed. During init of the operating system, the two shells are given their UART names and then started. And when the shells are started, the standard I/O is assigned, and then as with any process, only one shell is active at a time. The active shell's I/O is used to know where to get and send the standard request to. So when you are entering a command on shell 1, the system needs to know that it has to send the response back to shell 1 as opposed to shell 2. So that information is tracked here. So when you enter a command, the shell index that you entered the command on is captured in the structure. The key to making this work was in the process code. So when a new PCB is created, the standard I/O from the current shell is captured along with the arguments for the command. Next, the standard I/O for the current shell needs to be updated when switching processes. So when systic fires and you switch to a new process, the new process's standard in, out, and error handles are assigned to the current shell's in, out, and error handles. And here are the three functions that are used for in, out, and error. There was a problem that I got stuck on for quite a bit of time, and that's that not only do you need to update in the systic what the current in, out, and error are, but you need to capture what the in, out, and error are before you switch process in case they've been updated, so that if you happen to switch back, you're switching back to the overridden in, out, and error handles, not the what the original ones were. And that hung me up and created all sorts of mayhem in the system. So anyway, on to a demo. So here is one of my shells, and I have some commands over here that I'm going to just copy and paste in to create a file and open that for writing. And then I'm going to just put some text into the file, and I'm going to close the file. And one of the commands I implemented here was a cat command, so we could dump the contents of the file. Another command I implemented was a word count program, so I could pipe the output from that file to word count to get the number of words. And spawn also works, and that was quite the feat, getting these to run over and over again. It's kind of like banging on the keyboard and testing your program. That's where I found that bug. Now, word count takes a second parameter that allows me to block, basically, so it doesn't exit right away after running. So now I'm going to jump over to my second shell, and I'll show you that temporary pipe that I was talking about. So there's the temporary pipe that was created, and that word count program we can see is running here, and I can it's blocking, so I can wake it, and you can see it was released over there. And if I check this again, it's no longer running. And we can also see here if I can output to the text-to-speech converter and see if you can hear this.
This is a test. This is a test.
So that works pretty well. And one other piece I wanted to show you was with the named pipes. So I'm going to here create a named pipe called test that's got a 16-byte buffer. And now if I look at my pipes here, I should see test. And what I'm going to do is I'm going to write 20 bytes to my 16-byte pipe. And you'll see I write my 16 bytes and then block because it's a 16-byte buffer, so it's going to wait. Now if I come over here to my second shell and check, I'll see my pipe write running. And now I'm going to do a pipe read. I'm going to read 5 bytes. And that allowed the pipe writer to free up over on shell 1 and write out the remaining 5 characters. However, if I look at my processes, you can see pipe write is still running, and that's because I have it blocking the release. I can go ahead and continue to read my characters, and now I've read all of those characters, and so if I come back over here, it's no longer running, and I can see that over here too. I'm freed up, and I can now remove my pipe, and if I check that over here, it's no longer present. So that's my demo. Thank you very much.